In the previous video, we solved the equation 15 to the 4x minus 2 power equals 4 to the x minus 3 power. We left our answer as an exact answer, but using a calculator, we can convert this to an approximation of 0.1331. Now, you might recall in the previous video, I made some space by erasing one of the following problems. So I'm going to go ahead and erase some of this work so that we have that example back to work on together. In number 5, we have e to the x power is equal to 3. This is actually one of the simpler equations on this page for us to solve. It makes sense that because we have base e, we would take the natural logarithm of both sides. So we have natural logarithm of e to the x power equals natural logarithm of 3. Now the left-hand side is asking, what does the exponent on a base of e have to be in order to get e to the x? Well, obviously this is x. On the right-hand side, we have the natural logarithm of 3. Now this again is an exact answer. We can use a calculator to get an approximation for the natural logarithm of 3. You can use any scientific calculator to do this. I'm going to go ahead and use my calculator, and I get an approximate value of 1.09861. For number 6, we have 78 times e to the x minus 5 power is equal to 6. Before taking a logarithm of both sides, I want to write the left-hand side as a power only. So I'm going to start by dividing both sides by 78. So we have e to the x minus 5 power is equal to 6 divided by 78. Now if we take the natural logarithm of both sides, which is a better choice than the common logarithm since we already have an exponential expression with a base of e, we have natural logarithm of e to the x minus 5 power equals 6 over 78, which reduces to 3 over 39 if we divide by 2. On the left-hand side, natural logarithm of e to the x minus 5 power becomes x minus 5. Oh, this actually reduces further, doesn't it? 3 goes into 39 as well, so we probably can keep reducing this as 1 over 13. And then finally, if we add 5 to both sides, we get x equals 5 plus natural logarithm of 1 over 13. This is an exact answer. If we want to approximate this answer, again, we can turn to any scientific calculator. And I have mine here on the side. 1 divided by 13, and then natural logarithm, and then add 5. I get approximately 2.435. In number 7, we have e to the x minus 4 power times e to the 2x plus 9 power equals 15. We can simplify the left-hand side by combining these two powers into a single expression. You might recall that we can add the exponents in a situation like this. So we have x minus 4 plus 2x plus 9 as the new exponent on e. Let's simplify. We have 3x and then plus 5 as the new exponent. And again, it makes sense that we would take the natural logarithm of both sides since we already have a base of e. On the left-hand side, we get simply 3x plus 5. On the right-hand side, we have the natural logarithm of 15. To solve for x, we can subtract 5 from both sides. And then divide both sides by 3. So we have x equals negative 5 plus natural logarithm of 15, all divided by 3 as our exact answer. Again, we can approximate Using our scientific calculator, I have mine again here on the side. And so we have natural logarithm of 15 and then minus 5 and then divide by 3. I'm getting approximately negative 0.764. Now, a problem like number 8, I would treat differently than all of the examples we've been doing so far, because here I would use the fact that 25 is a power of 5 to rewrite this as 5 to the x squared plus x power equals 5 squared. Recall that if two exponential expressions are equal and they have equal bases, then their exponents must be equal. So we can write that x squared plus x must equal 2, or that x squared plus x minus 2 is 0. And now we can factor this as x plus 2 times x minus 1 equals 0, so that either x plus 2 is 0 or x minus 1 is 0, which gives us that either x is negative 2 or that x is positive 1. In either case, we should always check to make sure that what we think is a solution actually works. If we substitute negative 2 for x, the exponent on the left-hand side becomes 4 minus 2, which is 2, so that checks out. And if x is positive 1, we get 5 to the 1 plus 1 power, which is 5 squared. So both of these are true solutions. So it's important that you practice enough with examples so that you know what strategy would be most appropriate depending on the problem type. Don't fall into following a pattern for the sake of following a pattern. Use discernment in deciding which property to use where. Next, let's talk about how to solve logarithmic equations using the property that logarithm base a of x is equal to m if and only if a to the m power is equal to x. Remember that we can change between an exponential equation and its logarithmic equation companion by rearranging the three parts, the base, the exponent, and the result, which we call the argument. So here in this next example, we have logarithm base 3 of 4x minus 7 equals 4. If I convert this into its equivalent exponential equation, I can say that 3 raised to the 4th power must equal the result 4x minus 7. 3 to the 4th power is equal to 81. So we see that this becomes a pretty simple linear equation. I can add 7 to both sides and then divide by 4 to get that x is equal to 22. When you're solving logarithmic equations, it's really important that you check to make sure that what you believe is a solution actually is. If we substitute 22 in for x and we were to get a negative argument, we would have a problem. In this case, we're good because 4 times 22 minus 7 is 81, which is a positive argument. In the next example, we have logarithm base 6 of 5x plus 4 minus logarithm base 6 of x minus 3 equals 2. Before we convert this into an exponential equation, first let's combine the two terms on the left into a single logarithmic expression. Recall that the quotient rule states that we can combine the two arguments as a quotient. Now we have a single logarithm on the left and a fixed number on the right, so we can convert this into the exponential form. 6 squared equals 5x plus 4 over x minus 3. I said 3 and wrote 6. Let's correct that. 6 squared, of course, is 36, so let me go ahead and write 6 squared as a 36 to save some space. Multiplying both sides by x minus 3 gives us 36 times x minus 3 is equal to 5x plus 4. And again, we see that we end up with a pretty simple linear equation once we distribute. For the sake of space, I'm going to do 2 steps in one here. I'm going to subtract 5x from both sides and then also add 108 to both sides. So we get that 31x is equal to 112. Let's see, 112 divided by 31 gives us a decimal. So we can either leave this as an exact answer, 112 over 31, or write it as its approximate value of 3.6129. You always want to make sure that this does not cause either of the arguments to be negative. If we substitute 3.6129, the first argument is positive, and the second argument is positive as well, but that was close. All right, let's take a look at our next 4 examples. In example 3, once again, we want to combine the 2 logarithms on the left-hand side into a single logarithm. Here we're going to use the product rule to write this as, oops, I don't know why that got so small. Let's write this as natural logarithm of 9 times x squared plus 8x over 9. And let's distribute. And again, this is a single logarithm on the left and a fixed number on the right, so we can convert this into exponential form. Recall that natural logarithms are logarithms with a base of e. So we can write that e to the 0 power equals 9x squared plus 8x. E to the 0 power is 1. And it looks like we have a quadratic equation, so let's go ahead and clear one side of the equation by subtracting 1 from both sides. This is factorable. Let's factor this as 9x and x here. And let's do an 8 and a 1 here. And it looks like we're going to need to... Oh, that was not the right way to factor. Let's correct that. It's going to be a 1 and a 1, and then this one will have to be positive, and that one will have to be negative. Let me make sure I'm satisfied with that. 9x minus 1 times x plus 1 looks good now. All right, so we have either that 9x minus 1 is 0, which is 9x equals 1, or x equals 1/9, or that x plus 1 is 0, which gives us that x is negative 1. Here we want to make sure that both of these values of x make sense in the context of this problem and that neither one creates a negative argument. So we have the negative 1 I'm a little worried about. Negative 1 when squared is 1 plus negative 8 over 9. Okay, that one actually works too. So they both are true solutions. For number 4, we have a logarithm on the left-hand side of the equation and then another logarithm on the right. Let's get them on the same side. I'm going to create a little barrier here so we can keep our work tidy. So I'm going to write this as logarithm base 8 of x plus 6 plus logarithm base 8 of x minus 6. I'm just adding that to both sides is equal to 2. Use the product rule to write this as a single logarithm. So this will be logarithm of x plus 6 times x minus 6. Now we can write this in exponential form. 8 squared is equal to, and I'm going to go ahead and distribute the x plus 6 times x minus 6. This will be x squared minus 36. On the left-hand side, we have 64. And if I add 36 to both sides, I get that x squared is equal to 100. And using the square root property, I get that x is equal to plus or minus square root of 100. so that either x is equal to 10 or x is equal to negative 10. However, I immediately see a problem. I think that x equals 10 is a true solution, but when we substitute negative 10 for x into either of the original arguments, it causes the arguments to be negative. Notice that negative 10 plus 6 is negative 4, and the arguments of logarithms cannot be negative. So it turns out that this is an extraneous solution. It does not work. This really highlights the importance of checking what you believe to be a solution before declaring victory. All right, let's look at example number 5. Logarithm base x of 3 is equal to negative 1. Because we have a single logarithm on the left-hand side, we can convert this into exponential form immediately. The base x raised to the negative 1 power is equal to 3. X to the negative 1 power can be written as 1 over x. Right now, the x is stuck in the denominator, so let's multiply both sides by x, which would give us 1 is equal to 3 times x. And then if we divide both sides by 3, we get that 1/3 is equal to x. The base is 1/3. I don't see any violations, so this is a true solution. And finally, for number 6, we'll combine the two logarithms on the left-hand side into a single logarithm using the quotient rule. So we'll have natural logarithm of x divided by x plus 5 equals 4. We can immediately convert this into exponential form, recalling that a natural logarithm is a logarithm with a base of e. So we'll write e to the 4th power is equal to x over x plus 5. Now we have the variable in two different locations, the numerator and the denominator. Let's start to attempt to isolate x by multiplying both sides by x plus 5. So we have e to the 4th power times x plus 5 equals x. Let's distribute on the left-hand side. And next, let's try to get the two terms that include the x variable on the same side of the equation, leaving the other term on its own on the other side of the equation. So in this case, I think I'm going to subtract e to the 4th times x from both sides. Now I can factor out an x as the greatest common factor on that right-hand side. And finally, I can divide both sides by this binomial that x is being multiplied by. Here is the exact answer for x. Again, if you want to convert this into a decimal approximation, you just carefully have to use a scientific calculator to write 5 times e to the 4th power, all divided by the quantity 1 minus e to the 4th power.